Welcome back, my dear friends. So, we have seen the Milne-Thomson method to find an analytic function f of z if either the real part or the imaginary part is given to you. See, the Milne-Thomson method, have you noticed it? I do not know, but it was only given in the variables x and y. That means, when your function u and v is expressed in the Cartesian coordinate system. So, now suppose I give you a function in the polar form, that means in r and theta form. So, how do you go ahead and find the real part if imaginary is given, or else to find the imaginary part if real is given? So, here Milne-Thomson method does not work. See, main problem is you cannot express your f dash z in terms of z and then integrate it by simply doing z equal to z bar as in the earlier case. So, then how do you find the imaginary part? Suppose if I give you the real part and the function is expressed in the polar form, and since the method is not there, you use your property of analyticity. And do you remember the CR equations in polar form which we have discussed in the earlier session? So, the CR equations were UR is equal to 1 by R V theta and U theta is equal to minus R into VR. So, now suppose I give you a function u in terms of the variables r and theta, and I ask you to find f of z such that u plus iv is analytic. So, how do you proceed? So, since u is in your hand, you can find ur, and using one of the CR equations, in this case I use ur is equal to 1 by r v theta. Since ur is equal to 1 by r v theta, and this is true only because your f of z is an analytic function which you are trying to find out. So, I can express my v theta as r times ur. See, now I have got my v theta. What do I do next? I can find my v by integrating my v theta with respect to theta. So, once you get your u and v, then you can write your f of z as u plus iv. So, you can combine your function back, and by resubstituting z equal to r e raised to I theta, you can express your f of z in terms of z. So, let us see an example where you actually use this method to find your f of z. So, I am asking you to find v and also the analytic function f of z is equal to u plus iv. Both you have to find. You have to find the imaginary part and also the analytic function. F of z is equal to u plus iv. So, u is given to you as r plus a square by r cos theta. So, here you can see your u is given in the variables r and theta. So, we use the CR equations or the analytic property of u of the function f of z to find v. So, your ur is nothing but 1 minus a square by r square into cos theta. So, we will consider this. You can go ahead with either the first equation or the second equation in your Cauchy-Riemann conditions, but let us go ahead with the first equation here. So, my v theta is nothing but r times ur, that is r minus a square by r cos theta. Now, I have to find my v. So, I integrate this function on the right hand side with respect to theta. So, r minus a square by r is a constant. So, integral of cos theta is nothing but sin theta plus c. So, now how do I write my f of z? My f of z is u plus iv, that is nothing but r plus a square by r cos theta plus I into r minus a square by r sin theta plus c. So, if I combine those terms to get back my expression of f of z in z, I get my f of z as r into cos theta plus I sin theta plus a square by r into cos theta minus I sin theta plus c. So, you get this as r e raised to I theta plus a square by r e raised to I theta plus c. And you know that r e raised to I theta is the exponential form for your z. So, I can replace it by z, which is z plus a square by z plus c. So, this is how you find your f of z once u is given in the polar form. So, here you cannot apply the Milne-Thomson method as I have told you earlier. You will have to use the property of analyticity of your function to find your imaginary part and hence the function. Let us also see one more example. So, here also I am going to give you the real part and I am asking you to find what f of z, which is an analytic function. Here the real part u is minus r cube into sin 3 theta. Okay. So, you go ahead and find u r, that is minus 3 r square into sin 3 theta. So, you know that v theta is nothing but r times u r, that is minus 3 r cube sin 3 theta. Now, I integrate this function with respect to theta. So, minus 3 r cube into integral of sin 3 theta is nothing but cos 3 theta by 3 plus c. So, it becomes r cube cos 3 theta plus c. Now, again I need to express this function f of z as a function of z, not in terms of r and theta. So, I have my f of z as u plus iv, that is minus r cube sin 3 theta plus I r cube cos 3 theta plus c. So, I take an I outside because otherwise you cannot write an expression for z in terms of r e raised to I theta. So, I take I r cube outside. So, it becomes cos 3 theta plus I sin 3 theta plus c. So, what is that term inside the bracket? It is r cube e raised to I 3 theta plus c, which is equal to I z cube plus c. So, now your f of z is nothing but I z cube plus c, where c is the constant of integration. So, whenever you are given a function in the polar form, you have to use the analytic property of the function to find the imaginary part and hence your f of z, which is analytic. The same way you can proceed if either the imaginary part is given. Now, suppose I ask you to find the harmonic conjugate, as I have told you in the previous session. If you are asked to find the harmonic conjugate given any function, see, before proceeding to find the harmonic conjugate, make sure that the given function is harmonic. So, for that you have to check the Laplace equation. After that, you can use Milne-Thomson method obtain your function f of z first and then separate it into real and imaginary part to get the harmonic conjugate. So, if I give you u, you proceed, find f of z and then separate it into real and imaginary part and write v as the harmonic conjugate of u. The same is the case when v is given. So, now let us move ahead to orthogonal curves. So, how is orthogonal curves coming into picture in the analytic function part? Suppose I have a function f of z, that is u plus iv, which is analytic, then the curves u is equal to a constant, say u equal to c1 and v equal to c2 intersect orthogonally. So, how do you prove that? The proof is very simple. You have u is equal to c1, that is a constant, and v is equal to c2, a constant. So, if I differentiate to find the slope, say dy by dx, I get dy by dx as, I can write it as minus dou u by dou x by dou u by dou y. Let me call that as m1. Now, for the second curve, say v is equal to a constant, still you can go ahead and write your formula for dy by dx as minus dou v by dou x by dou v by dou y. Let us call that as m2. Now, to show that they intersect orthogonally, what do you have to prove? You have to prove that your m1 into m2 is minus 1. So, m1 into m2 in this case becomes minus dou u by dou x by dou u by dou y into minus dou v by dou x by dou v by dou y, which is nothing but minus 1. Why is this happening? This is because your fz is an analytic function and hence you have your CR equations in hand. Those are nothing but ux is equal to vy and uy is equal to minus vx. So, you can see that u is equal to c1 and u equal to c2 intersect orthogonally. So, whenever I have a function f of z which is an analytic function, your real part is equal to constant and the imaginary part is equal to constant, give you a set of orthogonal curves. Consider a family of straight lines passing through the origin given by y equal to m of mx, and the family of concentric circles x square plus y square is equal to r square with center at the origin, that is your standard circles with different radius. That means you are getting a set of concentric circles. So, these two families form orthogonal trajectories of each other, since each member of one family intersects each member of the other family at right angles. So, this is an example which will give you what orthogonal trajectories are. So, a family of straight lines y equal to mx, those are the set of straight lines which pass through the origin, and the family of concentric circles x square plus y square is equal to r square forms orthogonal trajectory to each other. Now, if we are asked to find the orthogonal trajectory of a family of curves, I give you a set of function, say for example, in this case we will consider say 2x minus x cube plus 3y square is equal to alpha. So, let us consider I am going to give you a family of curves 2x minus x cube plus 3xy is equal to some alpha which is a constant, and I am asking you to find the orthogonal trajectory to this family of curves. That means actually the result says whenever I have a function f of z analytic, this can be treated as the real or the imaginary part. So, let me consider this as u, the imaginary part of an analytic function f of z, because whenever your function f of z is analytic, u equal to constant and v equal to constant should be orthogonal trajectories to each other, or else they intersect each of the curves at right angles. That is the meaning of saying orthogonal trajectories to each other. So, how do I proceed and find out my orthogonal trajectory in this case? So, you can still use the Milne-Thomson's method here. you can write your f dash z. If I call this as u, you can either proceed it by calling it as u or v. So, here I call it as u. You proceed using Milne-Thomson method by writing f dash as ux minus iuy. So, then what do? You put x equal to z, y equal to 0, then integrate it with respect to z. Then you get your f of z in terms of z, which can be separated into real and imaginary part to get the orthogonal trajectory of the given set of curves. So, or else you can still call it as u, use the analytic property of f of z to get the imaginary part of f z is equal to u plus iv, an analytic function. So, let us see in this case what is your orthogonal trajectory to the given family of curve u is equal to 2x minus x cube plus 3xy is equal to alpha. So, I will proceed and I am going to use the Milne-Thomson method as I have told you. So, ux minus iuy in this case is 2 minus 3x square plus 3y minus I into 3x. Now, I have to put x equal to z and y equal to 0. So, my f of z or f dash z here becomes 2 minus 3z square minus I into 3z. Now, I will integrate this with respect to z to get your f of z. So, your f of z is nothing but 2z minus z cube minus I into 3z square. So, my f of z is the expression what you have got here 2z plus z minus z cube minus I into 3z square plus c. Now, how do I find the orthogonal trajectory in this case? Since you have started your function or the orthogonal trajectory, the family given as u, now I have to find v, that means the imaginary part in the expression 2z minus z cube minus I 3z square plus c. What do I do for that? I replace my z as x plus iy So, if I expand this, let me expand this to collect the imaginary part. So, I have x cube plus 3 x square into iy. So, the next term will give you 3x into I square y square. So, it becomes minus 3x y square and this becomes minus I y cube minus I into 3 x square minus y square plus I into 2xy plus c. So, if I collect the imaginary part of this, your v is nothing but 2y. From here, which are the imaginary terms you are going to get? It is minus 3x square y and plus y cube, and here what do I have? I have minus 3 into x square minus y square. So, this function v is the imaginary part of your f z such that u plus y v is analytic, and since whenever your function is analytic, you know that u is equal to a constant and v is equal to constant are orthogonal trajectories to each other. So, in this case this v is equal to say beta will be the orthogonal trajectory to the given family u is equal to alpha. Now, since the result is as such given to you that if f z is analytic, u equal to a constant and v equal to a constant are orthogonal trajectories to each other, let us verify it for a given function, say f of z is equal to z cube. So, I am giving you a function f of z is equal to z cube and I am asking you to verify that the family of curves u is equal to a constant say c1 and v is equal to a constant say c2 are orthogonal when c1 and c2 or any constants. So, f of z is equal to z cube. So, what do I do to find my x and y, sorry, u and v? I substitute z is equal to x plus I y, separate it into real and imaginary part. So, it is x cube plus I into 3x y 3x square y minus 3x y square minus I y cube. So, what is your u and what is your v? U is x cube minus 3x y square and v is 3x square y minus y cube. Now, how do I verify and check whether they are intersecting orthogonally to each other? So, for that, as we have done when I have explained the result, we need to find the slope m1 for the curve u equal to c1 and also for v equal to c2. So, how do you find it? For u is equal to c1, the slope m1, I call it as m1, that is your dy by dx. How do you find dy by dx in this case? Minus dou u by dou x by dou u by dou y. So, what is your dou u by dou x and dou u by dou y here? Dou u by dou x is 3x square minus 3y square divided by, what is your dou u by dou y? It is minus of 6xy. So, in the same way, I find the slope for the second set of curves or second family of curves, v is equal to say c2. In this case, your dy by dx can be written as minus of dou v by dou x by dou v by dou y. So, what do you get? Dou u by dou x, sorry, dou v by dou x by dou v by dou y, as in this case it is minus of 6xy divided by dou v by dou y is 3x square minus 3y square. So, you can clearly see that if I take the product of this two slopes, that is m1 into m2, it becomes minus 1. What does it imply? It implies that the family of curves u is equal to c1 and v equal to c2 intersects each other orthogonally or else at right angles. So, each member of the family u equal to c1 intersects each member of the family u equal to c2 at right angles, which proves that these are orthogonal trajectories to each other. So, we have clearly verified that the result is true for any analytic function. So, what all things have you learned in this session? We have actually started with finding the analytic function f of z if your function, the real or the imaginary part, is given in the polar form. We have seen that Milne-Thomson's method cannot be applied in the case because here you have to use only the analytic property. So, after that we have come to orthogonal curves and we have seen one of the important result which says that if your function f of z is orthogonal, sorry, if your function f of z is analytic, the real and imaginary part, if you equate it to constants, it forms family of curves which are orthogonal trajectories to each other. That means, they intersect, the family of curves u equal to a constant intersect the family of curves v equal to a constant at right angles. So, with this we come to an end of the complex variables which we have been discussing for the few sessions. We will be continuing with the mapping, the conformal mapping in the coming session. Thank you for listening to me.